Alright, so it seems like we're live. Yeah, so hi everyone. Yeah, I'm going to discuss the problems of the recently finished TOKI regular open contest 25, which has just ended. Sorry, give me a moment. I'm going to do something before that. Yeah, so hi everyone. Yeah, I'm going to. Okay, can you guys hear me? If those of you who can hear me can post in chat, that would be great, because that helps me to ensure that my voice and my streams are working fine. Yeah, but otherwise let's just go. Okay, I hope it's working. Okay, so first of all, yeah, I actually not a committee in this contest. I'm actually a participant, and I'm ranked 19. Yeah, so I'm going to discuss some of the problems from the perspective of a contestant. So this is not by any means like official editorial or something. Thank you. Yes, I can hear you. Okay, thank you. Yeah, I saw the chat. Yeah, while I'm doing this, I'm seeing the chat as well. So yeah, if you guys have any questions, feel free to drop it in the chat. I'll read it. Okay, so yeah, there are 8 problems today in 2 hours. So this is one of the TOKI Grow Open Contest, which has many problems and not so much time. So like in average, we have only 15 minutes to solve. If you want to solve all problems, we have only 15 minutes. So yeah, well, I think at least until problem G, which I read and tried to solve, I think yeah, it's not hard. I think it might be easier than traditional or like previous open contest. Maybe that's why they decided to the committee decided to have many problems and not so much time. Okay, so let's start from problem A. So okay, maybe I should switch to English, because I'm going to speak in English and I'm expecting international audience as well. So yeah, basically this problem, it just says that we want to run for n seconds, and every second we can either move back or move forward, and every time so that's in normal condition. But if currently we are at point X where k divides X and K is a given number, so n and K is given number, we can choose to go to 2X as well. Okay, so the main idea of this problem is every time you are at point X where K divides X, you can always go to 2X instead, and you don't go to X plus 1. And because K divides X, you know that K divides 2X as well, right? Because yeah, like if X mod K is yeah, I can write something here. If X mod K is 0, then we know that 2X mod K is 0 as well, right? So yeah, then it's not worth to just go to 2X, because I hope you can see what I'm writing. Because yeah, once we go to 2X, we can also, then this condition is still satisfied, and then we can go to 2X again, and then 2X again, and so on, right? So this greedy strategy works because like let's say this is X, right, and this is 2X, right? It's not like it is more optimal to go somewhere in between, because this is a multiple of K, and then you can jump 2X like that. It's here it is not worth to just jump here, because 2X is also a multiple of K, which means that you can also later jump 2X from here. So yeah, here you can just do that. So yeah, basically then the idea of this problem becomes very simple. You can just simulate it. If your current place is not a multiple of K, then you just do X plus 1. Again, it's not optimal to go backwards, because again, yeah, here we assume that we only move forward from 0 to K, and then yeah, we know that once, let's say we are here, then all of these are not a multiple of K, then there is no point in moving backwards, right? So you can just keep moving forward until K, and then you do 2 times repeatedly. Of course, when I say multiple of k, 0 does not count, because yeah, let's just say that 0 is not multiple of k, because like, yeah, if you do 0 times 2, then you end up still in 0, then you just waste your move. So yeah, let's not do that. Yeah, so and then the solution becomes very simple. You just basically simulate it, right? So if it's a multiple of k, and it's greater than 0, then you just then you just times 2, otherwise you just plus 1, right? And yeah, this is still it. Since it's 50, then the maximum output is 2 to the power 50, which, yeah, like I think the what I'm going to say, the worst case here is when k equals 1 and n equals 50, so that from 0 you go to 1, and then from there you keep doing twice, right? But then even if this is the input, then the answer is just 2 to the power 50, which fits in a 64-bit integers. That's why I use long here. I think if you use integer, you get overflow. So yeah, be careful with that, because the answer can be 2 to the power 50 or 2 to the power 49 maybe, because we use 1 second for the initial jump, right? Okay, so that's problem A. So yeah, that should be easy to solve. In I think the fastest solves it in 2 minutes. Yeah. Yeah, because it's just pure simulation once you manage to get the observation. Okay, problem B is a bit annoying. The idea is quite simple, but the detail might be a bit tricky. So the problem is about you are traveling, you are driving a car, and your initial speed is 0, and then you want to have n seconds. After n seconds, you want to travel exactly d meters, and every start of the second, you could either do this, right? You can change the velocity by at most 1, and it has to be integer, right? And then there's extra condition that your final speed must be equal to f, right? So yeah, actually this is easier if you take a look at the graph in the sample explanation. So this basically says that we can convert this problem by saying, like, we want an array. Oops, sorry. Is it possible to have an array of length n, right? And then let's say the first element, the zeroth element is 0, and then from the difference of ai and ai minus 1 must not be greater than 1, right? So, and then the sum of a is n, sorry, not n, d, I think. And then we want an to be f. So this is the problem, right? Okay. So yeah, we want, so by having 0 in the front, I mean, like, this first element must be either 0 or 1. Okay. Yeah, so this is basically the problem, because you can convert, like, every second is basically, if your velocity is v, then your distance will increase by v, and then you want the sum of the velocity in every seconds to be d. So you can formulate it this way, right? Okay, so let's discuss this problem first before I'm going to talk about why I spent 23 minutes on this problem and one wrong answer. Disclaimer, I'm going to be complaining about that, but let's just discuss this problem first. Yeah, so this might, at first glance, this might a bit scary. How do we, like, there are so many possible arrays. How do you check whether it's possible to construct an array with these 3 conditions? So I think first of all, we want to check what's the let's say we ignore this condition first, right? So let's say we don't have this condition. So we want to create an array that, such that the difference of each consecutive element is at most 1, and then the last element is f, right? Okay, and we want to know for every possible array that satisfies those 2 conditions, what is the minimum sigma a and what's the maximum sigma a that we can construct, right? Okay, so the minimum is simple, because, okay, at the very least, we want to have we have to have at most at least sum from 1 to f, right? Okay, because at the very least, because the difference of a consecutive element must be at most 1, then at the very least we have to have this sequence, right? Okay, because we want to end at f, right? And then, okay, we can do an initial check if n is less than f. So if if n is less than f, then this is impossible. Then this is, yeah, because the length is not enough for us to be increasing from 1 to f. And in this problem, it's not guaranteed. So we have to have this special check. In my solution, I just check it initially, like at the very start, because I don't want to be confused by that. So for the rest of my solution, we assume that n is at least f, and yeah, that means there are arrays that satisfies these two conditions, right? So we can construct an array that satisfies these two conditions if n is at least f. And now we want to answer these two questions. What's the minimum and what's the maximum? The minimum is this, and this is correct because we can just append zeros at the front, right? We can keep append zeros at the front such that the length of this is n, and this is the minimum sum of a that you can construct, right? The maximum is a bit tricky, and you can do this by doing the increasing at the front, right? If f is equals to n, if this is n, then this is the only array that we can construct. Then that's the maximum. But let's say the n is a bit longer than f, okay? Then we can actually do f plus 1, f plus 2, and so on, right? But then you must not do until all the way until n, but then you must do until like f plus, let's say the remaining of this is m. So let's say m is n minus f. Then you can do until f plus m over 2, because later after this you have to you have to go back to f. So you have to minus 1 f plus m over 2 minus 2 and so on, all the way going back all the way to f, right? So this is the maximum, right? This is the maximum sum that you can get, right? And if you think about it closely, you can actually create an array A that the sum is anywhere between these two, right? So let's say f is 3, and let's say n is 6. So I'm saying that if you want to maximize the sum, then we must do this, right? Okay. I think let's do even more to illustrate better. Then this is the maximum sigma A that we can get, which is what is this? 15, 7, 22. The sum is 22, right? And if you want to make, let's say we want to make 21, then we can just decrease this by 1. If you want to make 20, then we can decrease this by 1, let's say. If you want to make 19, then we can decrease this by 1. Okay, so you can see that if D is somewhere between the min sigma A that we have compute or max sigma A that we can compute, then we can construct the array. So it's just a matter of computing these values and these values. And these values is simpler, I just showed you. This simpler might be a bit complex because we need to, after f, we need to increase a bit, but you must not increase so much so that when you decrease, you can hit f at the end index. And fortunately, this f and n constraint is a bit small, and n is, especially n is small, so you can actually just again simulate the process. So what I do here is, if I loop from f plus 1 to n, and then if I try to increase it, I can still go back to f. Basically, this is just computation, like doing, if after I increase it, I can, with the remaining slots, I can still go back to f, then I increase it. Otherwise, I don't, and if I must decrease it, then I decrease it. Something like that, right? Okay, so yeah, if n is bigger, if n, I think n can be 10 power of 9 in this problem, can be up to 10 power of 9, then you have to do some maths on like computing the sum of this arithmetic series with difference one, and then when you go down, you have to compute the sum of this arithmetic series as well. But yeah, fortunately for this problem, we don't need to do that. So yeah, we can simplify the math a bit. Okay. Okay. Now I'm going to talk about what happened at this 33 minutes. So yeah, this problem has a very tricky case that, okay, I'm saying that yeah, the problem does not really explain, like, unfortunately does not really explain whether you can change your velocity at the very last second, right? At nth second. That changes the problem, because if you can change your speed at nth second, then let's go back to f equals 3 and n equals 7 case. This is 7, right? So if I can go back to if I can change my velocity at the very last second, then okay, let's choose 6. Okay. Then this array is valid because after the last second I can still decrease to 3, right? So d equals to 15 19 is a yes output. But if you cannot change the velocity at the last second, which actually what the problem is, then you cannot do this. Then the best you can do is just 1 2 3 4 4 3, which means that d is only can be up to 17, right? So yeah, this is and what I really annoyed about this is because I actually asked a clarification that whether you can change I asked in Bahasa, but this means that whether I can change a velocity at the last second at the nth second, and they said yes. So yeah, it's and this clarification is very early. I don't know whether we can get the timestamp of this, but yeah, it messes me up. And the only reason I aware of the actual problem is because the committee actually sent a Discord message to me, like actually was right after this answer was posted, but I don't check my Discord and I only read the answer after I submitted my first submission. So yeah, I lost, like, I don't know, I can't check the timestamp details anymore. So this is 24 and this is 30. Yeah. So I lost like several amount of minutes because of this, and of course I got 1 WA, which means 4 minutes penalty. Yeah. So because basically my first submission assumes that I cannot change the velocity at the very last second. And actually this is the thing with this platform is they don't allow they don't support changing clarification answer yet, and there's actually an open issue about this. So I guess that's why they send a message on Discord instead of changing their answer. I don't know whether that's really unfortunate. I don't know what kind of compensation they can give me. Anyway, so that's problem B. Let me think whether there's any more tricky cases that we need to handle here. I think that's most of the problems. Okay, so let's move on to problem C. Okay, so problem C, the description is quite simple. You are given n and you just want to find a positive integers a and b such that right such that sum of a and b times n is sum of their greatest common divisor and lowest common multiplier, and then there's a bound on what's the value of a and b must be, right? Okay, so this is the problem, right? So I'm going to be very honest. When I read this problem, my mind is a bit messed up because of problem B, because I do the problem sequentially and I don't read problem C until I solve problem B in this specific scenario. So when I open problem C, I already messed up my B and it's not like it's not the best contest for me anymore because of that issue in problem B. So I just want to try to solve this problem as quickly as I can with any method that I can, right? So the first thing that you do when you see a single input problem is you try to find a pattern, right? And it's true even for experienced programmers, right? If you can't think of a solution instantly, then you try to find a pattern, because doing such is very quick. I think I still have the code. So if you see this function, it's because you see that I don't end up using this function, because I write this function not for solving the problem, but I just want to see the pattern, right? And it's not very obvious how to get a and b in this equation, right? So I immediately straight up code solution to find a pattern, right? And this basically just initially I have this code. Initially I have this, right? And basically, yeah, you just look from 1000 to 1000. Sorry, I mean, A and B is integer less than or equal to 1000, and then you check whether there is an n that satisfies this, right? And if there, you can just, once you know A and B, you can just check whether this plus this is a multiplier of this, right? And then if it does, I try to print what's the n, right? And initially I don't have this as well, so I can show you what my thought process was. Yeah, so if I do this, the answer is very many. So I decided to do some kind of a memorization. So if n is already, we already get the answer for n, I actually break, right? Sorry, I actually don't print that answer anymore. Okay, so when I do this, we can easily see that, oh, for every n I got the answer, and one of the answer is just x plus 1. So if this is, sorry, I mean n plus 1, right? So a is n plus 1. And then the second number, you can always this. You can Google always for what, like 1, 5, 11, 19, 29. And it turns out you got like n squared plus n or something like that. I can't exactly remember. N squared plus 1 minus 1. Is that the formula? So 6 is, yeah. So we can do n and then n squared plus n minus 1. So this is one of the valid answer, right? So I already get excited when I notice this. Oh, I found a pattern that I can just submit directly without. Yeah, that's why I say, like, I just want to solve this problem as fast as possible with any valid solution. So I don't care about proving, because no one proves in programming contest. Yeah, I got this pattern. I can just submit. I don't know why it works, but it seems to work for several small value of n's, right? But the problem is n can be 100,000, and b cannot be exceeding 10 power 9. And yeah, when n is 10 power 5, then this value is large. It exceeds 10 power 9, right? So that doesn't work. So I have this code that for each, so the problem with the previous code is for each n, I try to minimize the I, right? Because if the way this loops works is, this loops for I equals 1, and then j from 1 to 1000 first before proceeding to I equals 2, right? So yeah, then this is the solution that we get. For every n, we found a solution that minimizes the value of a first, but the value of b can be very large, so we don't want that. So what I do is I try to minimize the maximum of the a and b first. So this is what we can do. We try to cap what's the maximum value of a and b first, and if we already find a solution with a smaller maximum of a and b, then we don't find a larger value. Then we got this, right? And here we can also easily see that for each n, the answer is 2n minus 1 and 2n plus 1, right? Yeah, and then again, it seems working. Then I don't prove it. Then I just submit 2n minus 1 and 2n plus 1, and then submit it, and then I got AC, right? So that's what I did, right? And I believe this is the intended solution as well, because it looks simple, and it makes sense, and yeah. And actually, let's try to prove this. So when I submit it, I don't really prove it, but I think it's not hard to prove this. So if we have n, right, 2n minus 1 and 2n plus 1, 2n is even, so this is odd, and this one is odd as well. And two consecutive odd numbers, let's say n is big, right? Let's say n is reasonably big, right? Because if n is 1, then this is 1 and 3. Well, it might still work, but I don't want to overcomplicate myself. But if n is big enough, and if n is small, we can brute force or do any solution, right? But if n is big enough, then we know that the GCD of these two consecutive odd numbers is actually 1. I don't know how to prove this mathematically, but actually it's easy. Yeah, of course. Actually, n must not be. It's not. I think any positive n works. So basically, yeah. Let's say by contradiction, assume that the GCD is not 1. Okay. Let's say it's k, for k bigger than 1, right? then okay, k cannot be 2 because this is odd, right? So odd numbers, of course, the GCD is not 2. So k is greater than 2 as well. This is not 12, this is 2, right? So this means that 2n minus 1 mod k is 0 and 2n plus 1 mod k is 0. Okay, but this is not possible. In order to have two numbers such that both of them mod k equals to 0, right? Then the distance cannot be 2. The distance must be a multiple of k. Okay, so if a mod k is 0, b mod k is 0, then a minus b mod k must be 0, right? But in this case, the difference is just 2. 2 is not a multiple of anything greater than 2. So this is impossible. So the GCD must be 1. Confirm must be 1, right? So that means, let's just move to next page. That means that the right hand expression, this expression, 2n minus 1, 2n plus 1 plus LCM 2n minus 1, 2n plus 1 is, so this is 1, we know this is 1, and LCM is basically just the product minus the GCD, and we know that the GCD is 1, so this is just the product, right? And this is 1 for n square, 2n plus 2n plus 1. Is it plus 1? No, minus 1, sorry. So this goes out and we just got 4n square. And then in the left hand side expression, we have 2n minus 1, 2n, sorry, this should be plus. 2n plus 1 times n, which means 4n times n, which is also 4n squared. So we just proved that this solution works, right? Okay. So, yeah, again, in programming context, you don't need to do that. As long as when you observe that it does seem to work until a reasonably value of n, and yeah, so that's what I do. But yeah, again, when I see the numbers, I don't actually prove it, but I have a hunch that it's correct, and it's not just because I saw that this pattern goes forever. It's because of, oh yeah, I think a difference, a GCD of number of two consecutive odd numbers is 1, and I think the math will cancel out, and then it just works. I have a hunch that it will be that way, so I just submit it, right? And it turns out that the math does check out, right? Okay, so yeah, turns out the solution is just a one-liner. Okay, so that's for problem C. Let's move on to problem D. And yeah, I don't have any problem with this. Any issues with this problem, I solve it in 6 minutes. Yeah, again, as I mentioned, in these 6 minutes, I tried to find a pattern. The first pattern does not work because the value of B will be very large. And then then I tried to cap the maximum of A and B, and then I got a solution that works, and I did it in 6 minutes. So yeah, cannot complain much on that problem. It's very smooth problem solving for me on that problem. Okay, for problem D, the question is, okay, this is starting to get a bit interesting. Not just like try to find a pattern or like, yeah. So there is a grid of size n times m, and this grid can be represented by, so we are not given the whole cells, the whole grid, but we are given like the values of each row and row and column, and the value of the cell is an addition of those two, right? So so yeah, if let's say, so we are given like this, let's say 101 and 0110, then okay, they actually didn't say the value of the cell is the summation, but they say that there is a flower if and only if, which my Siri is responding. There's a flower if and only if exactly one of them is 1, because here the cell is either 0 or 1, right? And they say that there is a flower only if and only if exactly one of them is 1, right? So yeah, you can see that here there is a flower here because there's exactly there's exactly one in this and this, right? And then here, because both of this is 1, this is not a flower, and then so on, right? Okay, and the question is, we want to choose a subsquare of size k times k. The question is, what is the maximum number of flowers that you can have, right, in this subsquare that you choose, right? So yeah, that's the problem. And then here we can't really compute the whole table because n and m can be 200,000. So if you try to put a whole table in a memory and then says that whether I and j has a flower, then that will be 200,000 square, which is too big, right? So yeah, we don't do that. Yeah, if we can do that, then this problem is not hard because it might be hard. No, it's not hard because we can just do prefix sum, and then for every k times k square, we can compute how many flowers in that, right? So I just illustrate my thoughts quickly just now. So if n times m is small, then we can try, let's say k is 2, right? This is not a flag, what I'm doing. We can just try how many flowers in this sub array subsquare, how many flowers in this subsquare, how many flowers in this subsquare, right? And to compute how many flowers here, you can use a simple 2D prefix sum, right? This is a classic problem. You can, if you don't know what is this, you can read about it. But yeah, you can query what's the sum of an elements in a sub rectangle in O1 time after doing some pre-computation, right? But the problem is the number of cells can be very big. N times m can be very big, right? It's big, right? So what we do is we don't compute the whole table. Instead, what we do is we actually try for each window separately. So let's say this is k, right? We know that for this sub sub interval, we can choose the subsquare there or there or there or there, right? Okay, let's say we want the x position to be in this position, right? So it can be here, it can be here, it can be here, it can be here, right? And similarly for this, right? So the thing is, the idea is because for each of these, regardless of where the x position of the square you want to be, the y position can be everywhere as well. So it's independent, right? Regardless of whether you want x to be here or here, the value of y can be anywhere as well. It doesn't matter, right? So now you want to find two intervals such that there are many flowers here, maximum number of flowers here. Okay. Now, how can we compute what's the number of flowers here by just looking at this and this, right? So we can do that simply by let's say there is a zeros here and b ones here. Okay, in this subrectangle, in this interval, right? And then there is a let me draw this properly. So a zeros, b ones, c zeros, d ones. Okay. Yeah, we can actually, the number of flowers here is actually just AD plus BC, right? So let's say this is the zeros, this is the zeros, and this is the ones. We know that every pair of zeros and ones, there's a flower here, right? Right. So yeah, we can do multiplication rule and say the number of zeros here multiply the number of ones here is the number of flowers here that are constructed by zeros here and ones here. And then for ones here and zeros here, it's just the other way around, right? Okay. So in other words, okay, let's say to make this easier, I actually reverse one of the array. So I think this array, I actually flip the input. So if 0101 becomes 1010, right? So now instead of AD plus BC, now I do AC plus BD. And this is simpler. Why? Because I can just do, let's say the sum of this is x and the sum of this is y, and sum just means basically how many ones are here and how many y's are here. Then the answer is just the number of flowers in this subrectangle is just xy plus k minus x times k minus y, right? Because yeah, again, k minus x is the number of zeros, right? Because the length of this is x, then k minus x is the number of zeros, right? Okay. So yeah, so that's how you compute how many flowers are in a subrectangle, right? But the problem is now there are n positions of x and n position of y. And if you want to try them all, then you go back to n squared, right? So sorry, I think one of these should be m, right? M positions of y, right? So we can't do that, but we have to do it a bit clever. And the observation is, again, I said that for every subinterval of k here, the range of this the values that we can get is independent. We can actually get all of them. So we can actually pre-compute one of them. Let's say this vertical ones. So let's say this is k is 3. So from y we can get 2, 3, 2, or 2, right? Right? We can get an interval that the sum is either 2 or 3, right? And the way you do this, you can do prefix sum or sliding window. That doesn't matter, right? So you can prefix, you can do I'm going to say, you can do pre-computation first of one of them, okay? And then you actually need to compute just the minimum and maximum. In this case, there are only 2 elements. You just compute 2 and 3, right? And then for every horizontal, you can also do the same, but you don't need to store it. So let's say 0 0 1 1 1 1 1 2 sorry 1 0 1 1 1 0 1, okay? And let's say this is after you already flip the input, right? So this 0 0 1 1 1 actually the initial input is 1 1 0 0 0, right? Okay, and then you know that the sum of this is 1, and then from these candidates of 2 and 3, let's say this is x, sorry, let's say this is y, let's say this is x. We want to find which y maximizes the value of this, right? Right. This might not be trivial, but actually, if you think about it a bit, if x is less than k over 2, then actually it's more optimal to also find the minimum value of y. So yeah, so if x is smaller than k over 2, the function will be like this, or maybe like this. I'm not sure. Yeah, so this is y. Y is a horizontal axis. I'm joking. What am I doing? And this is the value of this, right? And this assume x is smaller than k over 2. So the idea is, in quadratic function, we want to, it's more optimal to make one of the term maximum, because higher value have a much higher quadratic value. So if x is smaller than k over 2, then this value is large. We also want to make this value large as well. Even though this is small, it's fine. We want to make one of the term large, right? And yeah, so basically we know that if x is smaller than or equal to k over 2, then we just choose the minimum value of y. And if x is the other way around, then we actually want to find the maximum y. So we actually get this one instead, right? So the solution becomes simple. So yeah, this is what I do. I just scan A and B, and then now is the possible values of this, right? So yeah, I do sliding window, and then put it in this vector, right? And then I sort, and then I remove duplicates. This is actually not necessary. You can just keep it sorted. You don't need to remove duplicates. And again, you don't actually need to keep the whole thing. You can just actually keep the maximum and the minimum, right? And then I do another sliding window, but this time I actually want to for each value, I want to find what's the other value that maximizes the product, right? The sum of the product. And yeah, this is, yeah, again, this, I do this to flip the bits, right? And then if it's smaller than k over 2, then I choose the smallest value from the other factors. Otherwise, I choose the largest factors from largest value from the other factor, right? And then just print it, right? Yeah. So that's how this problem is, and I take 11 minutes to solve this. Yeah, I think that's a fair amount of time for me to solve this kind of problem. So yeah, I don't have anything to complain about this problem as well. Yeah, the only problem, the only issue I have with this contest is problem B again. It takes much longer than the level of the problem is, for me, shouldn't be 23 minutes to solve. Yeah, again, because of the wrong answer in the clarification. I'm going to keep blaming that. Okay, but anyway, let's move on. You're not going to watch me complaining about committees. I hope you want to see me solving problems. So yeah, let's keep doing that. we'll do div3 explanation tomorrow. I don't know. Tomorrow is big day, and I don't really have much time on. I have many other commitments on weekday, so uh, so yeah, I probably won't have time, but we'll see. I can't promise, and yeah, I don't really do div3 contests, so sorry about that, but we'll see. Okay, so problem. Water coder says this is educational for me, though I didn't participate. I'm not really sure what you mean by educational. I guess you learned something from that problem. Is that what you mean? Yeah. 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 I don't know what's the level of all of you guys, but yeah, I guess yeah. The good thing about this contest is there are many problems. So I guess people from various levels of expertise of programming contests have something that they can learn from. Like I think that there's just one problem that's just interesting for them, and they can learn something from that problem. So yeah, because I think the variations of these problems, the difficulty is very varied from. I won't say very easy. This is not very easy, but quite easy to hard, right? So yeah, it's a good learning experience for almost all of you guys. Okay, so problem E, it's a query problem. It's a data structure problem. It's a standard update query problem. So this problem, you have a tree with n vertices. And then initially there's a value, but this is not really important. Of course it's important. Sorry, it's important. But yeah, every vertex has an initial value, and you want to support a queue type of queue operations, and the first one is an update. So yeah, you can change the value of the value of the node by doing no, actually, if you're given x, then you want to change the value of all the neighbors. So you added by x, right? So let's say I think I can draw something. So let's say if this is the tree, right, and this is the value 1 2 1 2, right? So if you do an update of this node, then this becomes 3, this becomes 3, this becomes 4, right? Okay. Yeah, because every if this is 0, then it remains 0, because this is not the neighbor of this, right? So every neighbor of this node get incremented by its value, right? Okay. And the other operation is a query operation that you must again, you're given a node, you must output what's the sum of the value of all neighbors of x, right? So again, if I query this, then you have to answer 3 plus 3 plus 4, right? Which is 10. Yeah, 10. Okay, so that's the problem, right? Okay, so I can tell you what I tried, what I was trying in this problem first before I move on to my actual solution. So yeah, there is this common technique in this kind of problem that you can store the updates in a data structure. I usually call it pending update methods. And this solution will take q square root of q time. One of these q might be n, I'm not sure which one. But yeah, let's just say that q equals n for simplicity, because they can be up to 100,000, right? Okay, and the way you can do this is you can store all of the updates. So let's say there is a update of node 2, and then update of node 4, and then update of node 5. Instead of doing actual work in this thing, you can just store it in a vector first, right? And then if there's a query 6, then you know that the answer is actually the initial value of a6 plus whatever this thing might change the value of a6, right? So you can just iterate this data structure, and then if at least one of these if not at least, but if this node is actually a neighbor of this, then you must increment the value of a6, right? So let's say this increases by x, y, and z, right? So if 2 is a neighbor of 6, then you must increment by x. If 4 is not a neighbor of 6, then you do nothing. If 5 is a neighbor of 6, then you increment by z. You can do this. So instead of like doing actual work on the update, you keep it there first, and then when you query, you actually read whether which updates are relevant for this query. You can do that, right? But yeah, as you might notice, this might take q square, right? What are what if there are q over 2 updates, and then there are q over 2 queries, right? Then this will be very long, right? This will take every queries will take q over 2 time, because you iterate through the updates, and then it will be q square solution, right? So this technique actually does I don't know what it's called, but if the number of updates exceeds square root of q, then you must clean these updates and then like recompute all the failures in your data structure. So initially we have A1 and AN, right? But if your updates is big enough, then you must clear all of these updates and update the value of this, right? And the way you can do this is you can look through all the nodes, right? And then let's say this node, and then you can look through the neighbors and then see what's the sum of this update, right? So let's say on all these updates, this node is incremented by x and this node is incremented by y. So you can do like a of this, let's say this is I, you can do ai incremented by x plus y, right? This is what you can do. So so the analysis of this is the runtime of this solution is you know that for every query operations, it will take at most square root of q, because the number of updates you have in your data structure is maintained at most square root of q, and then the number of recomputation of this can be at most square root of q as well, because you only do this when your updates is at least square root of q, right? So, and then because there are q queries, the number of times you can do this recomputation is q divided by square root of q, which is square root of q. So this becomes q plus n square root of q, right? So this is what I found initially, but then there is a problem with this solution, because the update, the increment is not actually given. So when I presented this solution just now, we assume that the update is in this form. So update node, and then instead of plus ax, it's plus x, not actually x, but plus a constant, right? And the constant is given, right? If that is the problem, then we can solve it using this method. But the problem is the failure to be incremented is not given, and it's actually depending on what's the current value of ax. And this is a problem because we cannot keep a list of updates anymore, but because when we do update for, then we don't know what's the value to be incremented, and the value to be incremented might depend on the previous updates, and there's no easy way to compute that, right? So it's very tricky to do that, right? So yeah, we don't do that. So yeah, we can't solve this problem using this solution. But again, if instead of this is ay plus ax, instead of plus ax, if this is c, and c is given 1xc, let's say, and c is given, we can solve using this technique, right? But this is not how you solve this problem because of the one that I just told you, right? Okay, so the way to actually solve this problem is actually simpler than the pending update technique, because yeah, there's actually a simpler way. I just overlook it, and yeah, and I think the general idea that you can try to solve a data structure problem is segment tree, right? It's the general data structure to solve update query problems, because this is a very strong data structure, right? But the problem is with a segment tree, for every update you can do it on a consecutive intervals, right? You can only update from this to this, let's say. You cannot do like, oh, I want to update only the even indices. You can't really do that with segment tree. Okay, so and then the question is, because segment tree only can support that, how do you renumber the nodes? Again, renumbering indices in tree is very common technique. How do you renumber it such that for every node, the affecting nodes for every query, for every update, the affecting nodes is a consecutive intervals, or at least a constant amount of intervals, right? Because if it's small, then we can just update several times, update the segment tree several times, right? And turns out you can actually do that if you do renumber the nodes using BFS, right? So if you do this numbering, if we renumber the nodes in the tree using this way, then you can see that the neighbor of this is actually a consecutive numbers, right? Even if there's a child here, this is 11, this is 12, this is still consecutive, 5, 6, 7, 8, and the parent is also the neighbor, but again, you can just do 2 updates, right? So yeah, okay. And then in this, in segment tree, if you want to update a range, you can do what's called lazy propagation. You can read about it. I don't want to explain it here. But yeah, you can update a range, and then you can query a range as well. And then in this case, you can actually, before updating the index, you can actually query what's the value of A2 first, because we want to increment all of this by A2. And you can query this using this data structure, because again, segment tree, you can query anything you want at any time. You can update anything you want at any time, as long as it's consecutive, right? The indices is consecutive. So yeah, you can do that. And then yeah, that's just basically the solution. You renumber the tree using this way. And then for every node, you can first compute what's the real value of each A, because it might have been updated. And then you update this, and then you update this, right? And then if you want to do query, it's the same thing. If you query here, then you compute the product of these nodes, like the sum of these nodes, I mean. And if your segment tree supports sum operation, then you can do that, right? So yeah, I can briefly show you my code. So yeah, basically I copied AddCoder lazy segment tree library. It's a very good library that supports general use cases. So you can do summation, you can do a lot of things, right? So yeah, basically this is just copied from AddCoder, and then I need to specify some functions to use this library. It just basically says if I want to query from here to here, I want to actually compute the sum, not like the product or the maximum or what. I want the sum. So here I specified here that I want the sum, right? And then yeah, just okay. The code might be a bit complicated because you have to do the renumbering first, and then yeah. But once you do that, it's not very difficult. So if this is an update operation, then yeah, you can get what's the real value. You can apply it to its parent. Don't forget to apply it to its parent, because it's also its neighbor. And then you do it for the children, right? And then yeah, again for the children, you can compute what's the value, what's the index of this node after renumbering, and this node as well, and then do an interval. And then for the query, it's just the same thing, right? Don't forget to compute the A of the parent, and then compute what's the sum of all the A's of its children. Okay, so that's how you solve problem E, and this will take n log n, or again, one of these n might be q, but yeah, I think it should be something like this. Yeah, q plus n log n. Okay, yeah, because again with segment tree, all operations and updates and queries are log n time. Okay, so let's move on to problem F. Okay, so okay, this is actually an interesting problem. So the question is, you want to compute how many ways to go to tile n. So you are given n. Okay, t is just number of test cases, and the way you can jump is initially you are at tile 1, and then if you are at tile I, you can move to tile I plus x only if the GCD is 1, right? So if it's 5, let's say, if you are currently at 5, then you can jump to 5 plus 1. 5 plus, oh, okay, 5 is not a great number. Let's say 6. 6 plus 1 and 6 plus 5, right? So you can go to tile 7 and 11, because the GCD of 1 and 6 is 1, 5 and 6 is 1, and 2, 3, 4, the GCD is not, okay? So, again, this looks like a single input problem. So again, I tried to look for a pattern, but I actually didn't get it this time, because the pattern is very ugly, and even if I try to OS it, I don't get it. So yeah, I tried to compute a pattern. This is very easy to compute for small n. Doing a backtracking or yeah, you can solve it with DP, but you can just go the simple backtracking, because you just want to get for a small value of n, and then spot the pattern from there. But turns out this is not something that you can do in closed form. The pattern is not there. So yeah, we need to figure out something else, right? So yeah, we solved this problem using DP. right? So let's say we know, let's say fx is the number of ways you can go to x, right? Number of ways to x, and the number of ways is different. Two way are different if you fix it cell in one of the solution and not in the other one. So yeah, for n equals 5, the answer is 7 because of these various possibilities, right? Okay. Okay. So now, and we know that the best case is 1. F1 is 1. Yeah, there's only one way from to go from 1 to 1, right? And then for x, we can actually solve this by we try to iterate what's the last cell that we visit before cell x, right? So let's say yeah, so basically let's go back here. If you want to compute f5, we can try going to cell 4 first, and then from cell 4 go to cell 5, and then from cell 3 as well, from cell 2 as well, and then from cell 1 as well, right? So yeah, it's a summation of something of fi, and then if you decide to go from cell I, then the number of ways to go from cell I is fi, right? And then but then you have to check whether this actually is possible to go from I to x, right? So this is something like I x minus 1, right? But then this has to be checked whether so if the GCD of x minus I and wait a second, x minus I and I is 1, then you can actually do this, right? Otherwise it's 0, otherwise, right? Because yeah, 1 is the last, so this is x, let's say this is I, right? We can only make this jump if the length of this jump, if the GCD of the length of this jump and this and the current position is 1, right? We can rewrite this as GCD x and I, right? This is 1. This is equivalent statement. Yeah, because the way you compute GCD x I is you take x minus I and I, right? Okay, so now it is obvious to solve this problem in quadratic time, right? You can just compute fx and then you just loop this and then check GCD and blah blah blah. But then n is very big, it's 200,000, and I have a feeling that the reason that they don't hardcode the mod, in this case the mod is a variable, not like a constant number of like 900 million something, is because they don't want us to pre-compute what's the failure of the DP from 1 to 200,000 and put it in the source code, right? Because theoretically you might be able to do that. Like it will take time, but you can spend any time you want, and then once you have the failure, you can just put it in your code and then submit it, and then it will take constant time, it will take O1, and then you get AC, right? But the problem here is that the mod is a not constant, so you can't actually pre-compute what's the failure of the DP, right? Okay, so how do we solve this instead? So let me write again the equation. So we actually only want those fi that the GCD of I and x is 1, right? And we can actually okay, we can compute what's the prime factors from 1 to 200,000. Okay, and we know that a GCD of a number is 1 if they share a prime factor, right? If they share a prime factor, the GCD is not 1, right? The GCD is at least that prime factor, right? So you can compute what's the prime factors of all of these, right? So 2 is 2, 4 is also 2, 6 is 2 and 3 and so on, right? And 8 is also 2 and so on, right? And this you can do this with sieve of rs.ns, of course. You can do this with sieve, or you can just also do like for each I you loop until square root of I. It turns out it's very fast as well. Okay, and the number of prime factors, if you sum it up, it's not high, right? If you sum it up from 1 to 200,000, the number of prime factors is not that high, right? Okay, and it turns out you can also do yeah, this I don't know how to prove, but you can code up a simple solution to do code up a simple code to check this, that the number of 2 to the number of prime factors, this is like the number of prime factors of I, is also not huge. I think this is just 1 million or something, right? And this is actually the solution. So this will be the runtime of my solution. Okay, and the way we do this is so instead of considering all the i's that is co-prime with x, I actually take the other way and do this, and then minus I x minus 1 fi for gcd I x that is not co-prime. Okay, and the way we can do this is, let's say x is 16. This is easy because all the numbers that are not co-prime with this are those numbers that have 2 as their prime factors, right? So 2, 4, 6, 8, blah blah blah, right? So what we can do is we can store another array G. Okay, let's say Gi is the sum of f and I is a prime. So let's say this is no, it might not be prime, sorry. Gi is the sum of fx, where the product of prime factors of x is I, right? So when you do f1 is 1, right? f2 is also 1. Then you also increment g2 as 1, right? When you do f3 is I think 2. Then you also say g3 is 2, right? And you can keep this gi by basically looping what's the various so let's say f6, right? Let's not do 6. Let's do 30, right? Let's say f30 is x, right? Then you have to update g2, g3, g5, g6, all the various possible subset of this, right? g10 and so on, right? And then you have to increment this by x, right? Okay. And then when you do this is an inclusion exclusion principle basically. If you do a f30, let's say, you can do like the sum of f1 to f29, and then you minus g2, because we actually don't want those f that are a multiple of 2, right? And then we also don't want those f that are multiple of 3, multiple of 5, but then we're double counting those f that are multiple of 6 here, so we do this 10, and then we minus 30, right? So yeah, this is how you do this problem. So I can show you my code. This is when I do computation of prime factors just using linear loop. I don't do shift of apparatus times here. It's more complicated to code, and it's fast enough. So yeah, I just do that. And then so for every integer, I take all the subset of its prime factors, and then depending on whether there's even or odd prime factors that I'm considering now, I do either minus or plus. This is an inclusion exclusion principle. You can read a bit more on that if you're not familiar with it. And then once you know what's the value of fi, then you have to update the relevant values of g as well, and then you also need to consider all the subset of the prime factors of I, right? Okay, and then once you have this, you just, what's the n, you just answer it immediately, right? Very simple. So yeah, that's how you do this problem. Yeah, let me know if there's any questions. Actually a bit tired, so I won't explain anything in details because yeah, it's a bit late now, but yeah, I'll try to cover the general idea. If you don't understand anything, just post in chat. Okay, so last problem that I'm going to cover for today is problem G, mainly because I didn't solve problem H, and I even haven't read the problem yet. I read it briefly, but I don't understand what is it yet. So yeah, problem G, I tried to solve it, get wrong answers, but then I actually solved the problem after the contest ended in 3 minutes, right? No, not this one. Yeah. So the contest ends at 23:05 in my time zone, and I solved this problem in 23:08, which is very sad. Okay. So yeah, I know how to solve this problem, and we can discuss this problem. Why am I closing my Jamboard? Okay. I can solve this problem, so let's discuss this, right? Okay. So the problem is we have an array of size n, and then there's a permutation, and then we can do at most k operations, and for each operation we can do a interval, and then we can change all of the values in that interval to be the maximum, right? And then in this problem we don't actually want to simulate the operations. The operations are not given, but instead we are asked how many configurations of the final array can be, right? So yeah, the question is how many different values of B can be, values of A can be after all of these changes, and the changes can be anything, right? Right, okay. So yeah, let's say 3 1 1 2 3. The answer is 4, because if you do L equals 1, L equals 2, this becomes the array, and yeah, basically there are 4 different combinations that you can end up with, right? And we assume that you don't have to do all the operations. Anyway, you can just do L equals R, and then that operation won't do anything. So even if the problem is you have to do exactly k changes, the output is still the same, right? Okay, so yeah, and then what's interesting with this problem is the value of n and k is small, so you immediately thought of some dynamic programming, right? Yeah, so, and that's how I solve it. I think the solution is also like that, right? So I can go through this quickly. So yeah, so an observation of this solution is that the any final configuration will have the same relative position with the original array. What I meant is that if, let's say, the initial array is 5 3 4 2 1, then the answer will be there will be 5 elements, of course, in the answer, and it can be something like 5 5 4 4 1, right? But it cannot be like 4 1 4, something like that, or cannot be 4 1 2, right? So the answer must be several copies of 5 followed by several copies of 3 followed by several copies of 4 followed by several copies of 2 followed by several copies of 1, right? Yeah, because the operations are consecutive, and every time you do consecutive, you update all of this to be 4, and then there's just no way, if this is 5, you can jump over and then change this to 4. There's just no way, right? So the output must be in the form of several copies of 5, several copies of 3, several copies of 4, and then so on, right? So we can do DP, right? So the DP is, let's say, so the way I do is I do 3-dimensional DP, f, x, y, and z, okay? And this is how many so let's say this is y. How many different values can I put here so that let's say this is okay, and let's say this is 6, and sorry, let's say this is x. How many values can I put this array by only starting at this index, right? So I can only start with 3, or I can not start with 3, I can start with 4 as well, because I can choose to have 0 copies of 3, right? Okay, and then so on, right? Okay, what else I'm going to say? Okay, yeah, so that's the DP. Oh, Z is the number of moves that I can do, right? The number of operations left that I can do. Okay, so this looks complicated, but trust me, it's not. So let's cover up some base case first. So if y is equals to n, then this is just actually 1, because there's just no more cells to fill in, right? And if it's x else, this is else, right? If x equals to n, this is actually 0, because yeah, there's just no values left to fill in your cells, so there's just no way, right? And then else, so this is the best cases, and then else, and then again, right? let's say this is initial A. So let's say this is X, this is Y. Okay. Now we try to loop this element, how many copies we want to put this in, right? So let's say we want to put it all the way until here. So let's say this is I, right? So we actually compute the sum of I from Y to n minus 1. Okay, and it's just f x plus 1, y plus 1, z minus 1. Because in order to copy this element 3 times, you have to use at least one operation, right? Okay, of course there's a catch here. You can only do this only if maximum of ax to ai is ax, right? Because if there's you want to copy this to these 3 values, right? If there's a value here that is greater than here, let's say this is 4, this is 5, right? You cannot change all of this to 4 because, yeah, this is 5. No matter what you do, this cannot be smaller than 5, right? So yeah, so this is the DP, and there's one more special case. If y is equals to x, then you can actually just do fx plus 1 y plus 1 z. You don't use any operation at all to just keep it where it is initially, right? You don't actually need operation for that. Okay, so yeah, there's a special case. If y equals to x, you also take the sum of this, right? And then sum this, right? Okay, so this is how you do it, but there's still a loop here, and the state is already n squared times k. So this is already 27 million, right? If each of this is 300 cube is 27 million. And we cannot afford to do another looping. It's just too much, right? So I won't go into much detail, but the idea is that notice that for fxyz and for fxy plus 1z, the amount of looping is actually identical, because fxy plus 1z will do I from y plus 1 n minus 1, something that does fx plus 1i, right? And then z minus 1. Whereas this one will do sigma I y n minus 1 fx plus 1i. So the difference in these two terms is just the initial index, right? Because here it starts from y, here it starts from iy plus 1. So we can, to compute this, we can actually take advantage of this value, because this has done this loop. So this can just add in the first term, right? And that will be in constant time for each state. Okay, so yeah, that's the general idea, but there's a bit of detail that is a bit complicated. And yeah, initially I got RTE because of memory limit. Yeah, I do get that, because I think the memory limit is quite strict on this one. I don't know what the committee uses, but they say they are very relaxed. Yeah, because again I use n cube space, and n cube is 27 million. And if you I actually have 2 DP because of some sums that I need to keep as well. That's why it's just too much. And then when I try to do optimization using what's it called, crawling table, so that one of the dimension is 2, yeah, I accidentally have this bug where this mod 2 is actually outside the RAM. So this should be inside here, and I got AC when I do that. Yeah, so it's very unfortunate. And I solve it just 3 minutes after the contest ends. If I have the time I have from problem B that I shouldn't have wasted, I would have solved this problem. So yeah, again, I'm complaining about this contest. Anyway, yeah, so yeah, for those of you who have joined, I solved problem B in 23 minutes because I got a wrong answer on my clarification. Anyway, yeah, again complaining. Yeah, so those are the problems that I do know how to solve. Again, I haven't read problem 8, so I won't talk about that problem. Yeah, so yeah, but yeah, if you guys have read it and want to post it in comments or something, feel free. yeah, thanks for the stream. Yeah, thanks for watching as well, water coder. Not sure what the earlier chat is. Yeah, but yeah, thank you guys for watching. Yeah, I think it's been a smooth contest. It's the problems are great, except maybe there are too many counting problems. Almost all of them are counting. So problem, this is not counting, this is optimization. But like problem B is, no, problem B is also not counting. But problem C is also not counting. What am I saying? This is also not counting. But F is counting, and G is also counting, and I think H is also counting. No, H is not counting. Sorry. So F and G, but still it's a bit annoying. Yeah, this is not counting actually. Why am I thinking that there are too many counting problems? Okay, maybe not. But yeah, yeah, again, problem B. They never say we cannot change the velocity at the very last second. Yeah, so thanks for the stream, Joshua. Yeah, thanks for watching as well. And yeah, yeah, so I hope you guys enjoyed it. So yeah, the editorial is actually up, so you can actually read this as well. Yeah, but I just explain how do I solve them. Some of them might be different with an official editorial. And yeah, again, I haven't read problem H as well, at all. I mean, I haven't read problem H at all. Okay, so yeah, yeah, thanks to the organizers, I guess. Again, it's good problems. Yeah, it's only if you can answer my clarification correctly, then I don't have anything to complain. But yeah, that wrong answer on this clarification takes me like maybe 10 minutes, and then a 4-minute penalty. I should probably be able to be like 16th place or something. But yeah, and okay, of course I will be able to solve G, then I might jump like all the way to 10th place or something. Come on. Yeah, okay, but anyway, yeah, let's end this. It's getting pretty late. Yeah, thanks again for watching, and see you all next time.